So if you went into the resources for this session, you notice that there were only 2 slides available, and that was by design. That was on purpose. All of the slides will be shared the second this is over. I'm going to drop them all into the slideshow, and you'll have access to all of the resources and links that I have included in the presentation. But I'm really worried about spoilers. I don't want anything to be spoiled. So, I wanted to be careful. You couldn't see things ahead of time and have all the answers. We got to be careful about those things. So welcome. I have titled this session Always Isn't Forever. And you might have seen from the description, the purpose behind that or the reason behind that is I wanted to talk to you today about some rules in math that often students either create themselves or we unintentionally push them to understand or push them to hold on to that don't hold true forever. So at some point in their career of math, they will realize that these rules don't hold, and they probably will be pretty upset about it, and they'll be confused. And so we're going to talk today about some of those rules. Just a little bit about me. My name is Katie O'Gorman, and I currently am the instructional coach for math in the elementary at the American School Foundation of Monterey. And so math is my favorite. All I ever want to talk about is math. So I'm glad you're here, and I hope you want to talk about math today too. This will be somewhat interactive. There will be some opportunities to go into breakout rooms and talk about your thinking. So I hope that you're open to at least unmute yourself in those situations. It's up to you whether or not you want to turn on your camera. Okay, so as a kind of a starting point for this session, I wanted us to think about this quote from Marilyn Burns, who is one of my favorite math educators. And so I look for an opportunity to include her in as many of my presentations as I can, especially for those who may not know of Marilyn Burns. I think she's a really good one to know. So it says, a major goal of mathematics instruction is to teach for understanding so that students build a foundation of mathematical knowledge. But, and this is why it's in bold, but teachers can't teach for understanding if they don't have a firm foundation of understanding themselves. And so this whole session is built around that idea that it's really important as mathematics educators that we understand the math we teach very well and do what we can to understand it even better so that we can be the best teachers for our students, right? Make sure, again, kind of back to that main point of we're not teaching them anything that will expire, that will not hold forever. Okay, so what I'd like for you to do while you watch this video, it's only 1 minute long, it's very short, is I'd like you to write down any observations you have about what's happening in this video. So this is a video of a teacher doing an assessment with a student, and the student shares her thinking with her. And so take a moment, as you're listening, to take down any notes, anything you noticed from this video.
Here's a word problem. There are 295 students in the school. School buses hold 25 students. How many school buses are needed to fit all the students?
Okay.
So how many school buses?
320.
And how'd you figure it out?
Well, when you read it to me, you figure out what is the number that tells you all the information, like if it's adding, subtracting, multiplying, or division. And since I heard all, I figured, oh, that's plussing. So I plus 295 and 25, and I got 320.
Okay.
Okay, so here's what we're going to do. I'm going to put you in a breakout room. This will be the breakout room. For the few breakout rooms we do, you'll be with the same people, theoretically, as long as everyone stays in the session or if we don't have anyone join. So in your breakout room, here's a couple of things I'd like for you to do. The first thing is, as it pops up and tells you you're going to a breakout room, just scribble in the corner the number that you have. It's going to help us when we come back from the breakout room. Take a moment to introduce yourself, who you are, where you teach, what you teach, and then share your thoughts about this video. So specifically, what would you do next with this student based on what you saw in the video? And then how might you prevent the thinking that you saw with this student with future students, right? How might you think about this a little differently so that other students don't hold on to this understanding? So let me get the breakout rooms going. Welcome back. Welcome back. We'll make sure everybody has a moment to get back into the main room before we keep going. I think the room should be closing any second if it hadn't already. Welcome back. For those that joined us just before we started the breakout rooms, I think it might be helpful if we all watch that video. It's only, like I said, it's like 45 seconds long to kind of refresh what we were talking about so that our conversation can make sense. So and then you'll see what the next step is. So this is the video we are talking about here, and this might give you a good refresher.
Here's a word problem. There are 295 students in the school. School buses hold 25 students. How many school buses are needed to fit all the students?
Okay.
So how many school buses?
320.
And how'd you figure it out?
Well, when you read it to me, you figure out what is the number that tells you all the information, like if it's adding, subtracting, multiplying, or division. And since I heard all, I figured, oh, that's plussing. So I plus 295 and 25, and I got 320.
Okay.
Okay. So what we're going to do, this is something I picked up from a Doug Fisher workshop. If you've not attended one of his workshops, I highly recommend it. Is I asked you to pay attention to your breakout room number. So I'm going to spin the wheel. We'll see what number comes up. And if someone from that group would like to share what you discussed, we would welcome you to unmute and share. This one's fun. I like this particular spinner. So this is wheelofnames.com, by the way, if you're wanting to use this resource, very easy to use. Would anyone from group 7 like to share what they discussed about this video or what they were wondering or any of those thoughts? Just feel free to unmute.
Well, we were talking about that it's kind of difficult word problems, especially we were saying that we work on bilingual schools, so their vocabulary, it's pretty hard for them, especially when they are on the first graders. You know, they need like drawings, something they can see visually. I think it's easier for them because the words, they can just get mixed up.
Yeah, for sure. Thank you for sharing. Thank you. Okay. Would anyone else like to share? We're a fairly small group, so if there's anyone else that found something interesting from that group, we can take maybe one more comment, or from that video, I'm sorry, if you'd like to share.
In our room 4, my team and I were sharing that it's important to scaffold the students with the meaning of the words so they can understand before they actually do the problem. So especially because, as you mentioned, we are teaching students, we're teaching English as a second language. So that's important. In fact, 2 years ago, I don't know if you were in there in Live Curious, in the keynote, the presenter showed a video of a student in United States that he was taking a test and he couldn't understand the word problem. I will try to find out that video. I don't remember the name, but I will share with you. So
that would be great. Yeah.
Okay.
Okay. Thank you for sharing. Thank you. Okay. So this particular video is going to kind of lead us into the main part of the discussion today, which is what are some of those rules or things that we teach to our students that don't hold forever in math, that always isn't forever idea. And so I really appreciate your sharing, and you're right, especially in schools, in the schools that most of us are in, where English is not the first language of many of our students, that can already be a layer of challenge. And so something that we like to, or that we often do, is we like to teach keywords, and we like to tell them that when they see certain words, it means a certain operation. So you saw in that video, that girl had taken the idea that the word all meant for her to add. And so she really did not read for understanding, or maybe she didn't understand the problem and she just saw the word all. So she took the two numbers and she added them together because that's what she either had internalized from years of doing word problems, or someone had taught her that keywords in a problem can tell you what operation to do. And the problem with that is that at some point, either there's a couple of things that could happen. Either the problems will become so sophisticated that those keywords don't mean the same thing, right? So like in this example, this isn't an overly sophisticated problem, but it's almost like whoever wrote it with the purpose of seeing if the student got confused by the word all, right? If they could read it and understand what the problem was asking them, or if they had already internalized this idea that there's a word in the problem that'll tell me what to do, so I'll just use that word and I'll take those numbers and I'll add them together. And so, what we find is that as students get older and they either get more sophisticated problems, such as multi-step problems, or they just get problems for which the keywords they've been taught don't mean the same thing. And so what ends up happening is they misapply those rules, and then they have to basically relearn how to solve number stories, how to solve word problems, because someone has told them that all you have to do is pull out a certain word and do something with it. And now they've got to learn all over again. That's not really the case. You need to read to understand. And so what we want to be doing is teaching students to read to understand the problem. And, someone mentioned in first grade, that's particularly challenging, but drawing a picture and pulling out manipulatives, acting it out, those are, viewing it as a story, those are all things that are going to help the students understand what's happening in the story and to realize that a certain word isn't necessarily just going to tell me what to do. So each time we do a rule or an always isn't forever is what I'm calling them, you'll see there's a rule that at some point will expire that will not hold true forever. You'll see when it can expire. In this particular case, I feel like it can expire really any time, but third grade is when there's a standard for students to solve multi-step number stories. And so the minute you've got more numbers and more things happening, that's really going to throw them off. They're really not going to know what to do if all they've been taught is to look for keywords. And then you'll also see on some of these slides, I've got a resource. And so once this presentation is over, you'll have these slides and all of the links. So in this case, there's an article called Avoiding the Ineffective Keyword Strategy. And so, that can give you a little bit more information. So I thought that was a good place for us to start, because this is true no matter what grade you teach, right? We want to be careful that we're not teaching our students that all you have to do is pull out a certain word and pull out the numbers, and that'll tell you what to do, because that's not really true, and that's not going to hold true for them. Okay, here's our next rule. So this time, and this is what I'm going to tell you though, don't put your answers in the chat until I tell you, okay? So here's your next problem. I want you to try to solve 26 times 10. Solve it the way that works for you, or the way that you've taught it, or the way that I would encourage you to think how you would solve it or how a student might think about solving it. So I'll give you a moment. Don't put any answers in the chat. Okay, here's what I'd like for you to put in the chat, but don't hit enter until I say go, okay? I want you to put in the chat how you solved this problem. The answer is not important. How did you find the answer to this problem? In a few words or a sentence, but don't hit enter yet, okay? I'm gonna open the chat so I can see it. Okay, so take a moment. How did you solve this problem? I'm sorry? Oh, okay. All right, so this is another Doug Fisher. Oh, my computer has decided now is the time to update Acrobat. That is super helpful. Great timing, computer. Okay, there we go. Let me actually, hold on, now it's being difficult. Okay, so while my computer decides how to behave, in the chat, you should have already written it. I want you to hit enter. Oh, shoot, I don't know why close it and just try again there. Okay, take a moment while my computer, like I said, decides to behave. And take a look at what people have put in the chat. Do you notice any commonalities among the chat? So I'm seeing here, add a zero, add a zero, add a zero to the end of 26, add a zero, add a zero, add a zero, add a zero. Oh, wow. Add a zero, add a zero, add a zero, add a zero. Okay, I'm seeing a lot of add a zeros. So my question for you is then, how would you solve this problem? Take a moment, solve this problem. Will your rule still work? Share your thoughts in the chat. You don't have to wait for me to tell you to this time. Share your thoughts in the chat. Will your rule still apply? Why not? Or why? Okay, so I'm seeing some people, moving the decimal point, moving the decimals, becoming a common piece of this. So, in this case, Lisa put different rule. Okay, so this is where we need to be careful because students don't always understand that different rules apply in different situations. So what we want to be careful of is that we don't tell them a rule that will then have to change, right? So that later someone's going to have to say, yes, that's true only when, right? We want it to be something that mathematically is sound. So here is the rule that people have been telling. When multiplying a number by 10, just add a 0 to the end. But you just saw that rule does not hold, right? You saw it right in action. Almost everybody put in the chat, add a 0 to the end. Now, we know as adults that when we get to decimals then, that doesn't work anymore, right? You look at it, you throw the 0 on the end of 2 6/10, that doesn't change the number. But a student may not understand that. And so what we want to be making sure we do is teach them the mathematical foundation behind why does that 0 seem to appear there? Well, it appears there because the place value changes. When I multiply a number by 10, everything shifts to the left one place. So if they have that understanding, then it won't matter that they get a problem like this because they'll just shift the numbers to the left for every multiple of 10 that they're multiplying, right? 10, if they do 100, they'll move it 2 places to the left. If they do 1,000, they'll move it 3 places to the left. They'll understand, and then they'll be able to apply that understanding when they divide by 10 or divide by 100. They'll have that understanding that this works no matter what the numbers I'm dividing are, right? And so what we want to be careful of in these situations is kids will often learn the multiplying 26 times 10 first. And so they'll either be told that rule or they'll internalize that rule. And so then they'll get to the decimal multiplication and be like, everything I know is wrong, right? So we want to be careful that they don't get to that place where they have to undo a rule that they've fixed in their mind, right? That we, from the very beginning, get them to understand when you're multiplying by 10 or a multiple of 10, what's actually happening is the place value is changing, right? Not even the decimal is moving, right? It's the place value is shifting. And you'll see down at the bottom, there's another article, and I really enjoy the title of this article. It's when you multiply by 10, just add a 0? Horrors! So it's a very short blog post that gives some more information about why we want to be careful of, keeping that rule on kids. Okay, so we're going to shift gears again. All of these rules, so I'm just telling you now from the beginning, all of the rules in these boxes expire, every single one of them. Always subtract the smaller number from the larger number. That expires at some point. Always divide the larger number by the smaller number. It expires. Addition and multiplication make numbers bigger. Expires. Subtraction and division make numbers smaller. Expires. So here's what I'm going to ask you to do. And I'm going to give you a moment to do it before I put you in a breakout room to talk about this. See if you can come up with a problem or a situation that proves that this rule expires. So I did that to you on the last problem, right? I told you 26 times 10. I let you tell me what you did to solve it and the rule that you used. And then I kind of pulled the rug out from underneath you and I was like, that rule does not hold, right? Always isn't forever. So what I'd like for you to do in this situation is come up with an example of a rule or of a problem that shows that one of these rules expires. Pick any of the 4 that makes the most sense to you. So I'm going to give you a moment to look at the rules, to think about it and start kind of making a note about it. And then if you have trouble coming up with one, that's totally okay. I'm going to put you in a breakout room to talk about it with a couple of other people. So take a moment. Like I said, I'm going to be quiet. Take a moment, pick a problem, start trying to come up with a problem that proves it wrong. Okay, very short breakout room. All you're going to do is share if you came up with an idea of an example of a problem that would prove one of these rules to expire, right? That would show that this rule expires. So short breakout room, you're going to be with the same people except Patty Rock. I'm just giving you a heads up, you got moved in a room. Okay? Okay, welcome back. So I kept that one very short. You may not have had enough time and that's totally okay, but I just wanted to give you a moment to talk about if you had any rules. So I already told you these rules expire. So what we want to look at is if anyone has come up with examples of how they expire. So let's start with, oops.
I got one.
Okay, hold on. Patty, I love you. So hold on one sec, Patty. I'm going to go one by one through each of the rules.
Fine.
You're awesome. All right, so the first rule was, or let's see, was that? Yeah, that was right. Always subtract the smaller number from the larger number. So if you came up with an example of a problem that's a counterexample or proves this wrong, or proves that this doesn't hold, drop it in the chat for us. And if you came up with one for another one, be ready to drop your example in the chat as well, because I didn't give you a lot of heads up on dropping it in the chat. So if you have an example for always subtract the smaller number from the larger number of when that's going to expire, drop that in the chat. So what have we got so far? Mirna, 8 minus 10. Yep. 3 minus 10. Yep. So as you can see in the, and we'll see if any others show up, but as you can see, negative numbers and decimals, right? So the big thing is when this shows up is when we start working with rational numbers. So when we start getting into negatives. Or in some algebra situations, yes, for sure, right? And that's where we're going to see some rational numbers. So basically, the appearance of negative numbers is going to be the big reason why this expires. So we want to be really careful that when we're teaching, so I know some people then say, okay, but I teach a younger grade, and what am I supposed to say to them, right? They're going to mix this up, and I need to be able to explain it. And so it's okay to help them. So a couple pieces. One, this is why we want to avoid too many situations where we have what they call naked numbers, right? Where there's not a context for what they're subtracting and why, right? So if you're teaching kinder, first, second, when you're doing subtraction, and this is the knee-jerk reaction is to correct them, is you really want to be thinking about what kinds of problems you're asking them to do. Because if you're giving them problems that are, right, so if you're already giving them the problem, 23 minus 10, then it's already set up for them. And if you're not, then you can help them work through it by going back to the problem and saying, okay, well, Katie had 10 apples and she ate 2 of the apples. So let's think about what's happening in this story, right? So it's going back to the story and helping them build that foundation. The thing that I've found that when I'm working with teachers and we're trying to come up with games is that subtraction games can get really tricky if you're setting up a situation where they're rolling a dice maybe or drawing cards, is then they have to figure out the order. And so what I've been putting into those games instead is students finding the distance between the two numbers. So putting them on a number line and thinking about how many jumps are between them. So then it's not about setting up a subtraction problem necessarily. It's helping them understand there's a difference between these, or there's a distance between these. And it doesn't really matter what order I write the numbers in. I just need to know what that distance is. Okay, so in the same vein, always divide the larger number by the smaller number. So when does that happen? When does that expire? I thought Patty was ready. You have 2 pizzas for 8 students. How much pizza will each person get? Absolutely. So, this is a situation where we have fewer items than we have people. And so what's going to have to be shared is it's going to have to be divided up more than what we have, right? They're not each going to get a whole pizza. 2 divided by 10, Vicki, yeah, decimals. So you can see in the example, when it expires is 5th grade, and it's operations with fractions and decimals, right? Really any operations with numbers less than 1, or in situations where, yeah, you might need to divide, like the example Patty gave of the pizza. Another great example, Lydia, with the 4 divided by 6, 4 over 6 means 4 divided by 6. So while we want to tell the kids, same thing in like 3rd grade, when we start doing division, we want to tell them to put that bigger number first. What's going to be more important is to help them understand the context of the story, right? So that then when they get to a situation like what Patty gave of the 2 pizzas divided amongst 8 students, they don't immediately knee-jerk reaction 8 divided by 2. because they've been told to divide the bigger number by the smaller number, right? And so that some kids will just automatically do that, even if the problem clearly is not telling them to do that. And so that's where we want to go back to the context. What's actually happening here is the pizza is getting shared among the students, right? I'm cutting up the pizza and sharing it. Okay, doing great. What about addition and multiplication make numbers bigger? What's an example of when that would expire, or a situation when that might expire? This is another one that I don't know how much, as we wait to see if anybody puts in the chat, I don't know how much people are actually saying this rule versus maybe letting students believe it and not correcting it when it happens, right? I mean, I think it probably is happening, but I think more than anything, it's happening, the students are developing their own understanding of this, and we need to work to make sure that's not what's happening. Okay, so yeah, multiplying with decimals, multiplying by fractions, right? Fraction by fractions. I see a question about examples with negatives. Yeah, so what if you're operating with rational numbers, right? So that's another time that it expires. So the first time it expires is 5th grade. It'll expire again in 7th grade when they're doing operations with rational numbers, with negatives. And suddenly now they're getting answers that could be negative. And so the answer isn't getting bigger. The answer is getting smaller. Absolutely. You guys are killing this. Oh, it's like a game show. I wish I had money or something to give out. Okay, so last one. Subtraction and division make the number smaller. So it's going to be some similar examples, right? You may have another example to put in there, but it's going to be a lot of similar examples of when this would happen. Okay, any specific examples before I move on? Not seeing any in there. I think, like I said, there's enough similarity. Okay, last rule we're going to discuss today, okay? This is the last one. So it says, Alexis, a 1st grader, was given each equation below and asked to determine if the equation was true or false. So spoiler alert, they are all true. So why is it then that Alexis put false on some of these problems? So take a moment, take a note if you figure out, don't put it in the chat because I am going to have you talk to people about it. Write yourself a little note. Why is Alexis putting that some of these are false when, as I've told you, they are all true? Take a moment and then I'm going to put you in your last breakout room for today. Set up. All right. Another short little amount of time. You're just sharing with your partner or group. I'm sorry, I did not get to this part. Okay, so why did Alexis put that there were equal, or they were some that weren't equal? So what I want you to do with your group is I want you to try to write an always isn't forever rule. So you've seen some examples of the types of rules. What is the rule that Alexis is holding on to here that will not hold true forever? All right.
Of course.
Welcome back. Welcome back. I hope you were able to have a good conversation. I know it wasn't very long. I want to be careful I'm not leaving you in these rooms too long, right? Let you have your discussions and then come back. So before I start sharing the screen again, what I'd love is if you could go to the chat, and we're going to do the waterfall again, and type in what rule do you think that Alexis, and if you don't have an answer, that's okay, but what rule do you think Alexis is holding on to right now that's causing them to write false on some of those problems? So prepare the chat. Don't hit enter yet. It's part of the fun is you get to see the waterfall of answers. Give me a second. I hear the sounds of typing. That's perfect. Okay. If you're ready, I want you to hit enter in 3, 2, 1, go. Oh, there's a little bit of a slower waterfall this time. That's all right. We're all right. Okay, so let's see. Equal sign means an answer, a result instead of.
I couldn't finish.
Oh, that's okay, Mira. Oh, you couldn't finish before I told you to hit enter?
Yes.
You're such a rule follower. You hit enter even though you weren't done. Yes, what were you going to say, Mirna, instead of what?
Instead of having an equal form of showing the two sides of the equal sign, meaning the same.
Okay.
I didn't know how to word it.
That's okay. That's okay. All right. So the place of the equal sign's not always on the right. We'll put together groups of objects, order of the equation. The answer comes at the end of the equal sign. So you were all noticing there were some issues that they were having with the equal sign, right? That's the problem here. So when you look at them again, after kind of seeing that in the chat, and you take a look through Alexis's answers, each of the ones that they said were true are the ones in the probably the, for lack of a better word, the like standard traditional, probably how a lot of us saw problems being written, which is there was some kind of operation, the equal sign, and then the answer, right? And then any situation where that wasn't the case, Alexis got confused and was like, no, that can't be true, right? So you see on number 2, 8 equals 2 plus 6. On number 4, 1 plus 9 equals 5 plus 5, right? And so that one in particular is a great example of what Mirna was saying about how we need that balance on either side of the equal sign, right? And so there's clearly a misunderstanding about the equal sign in this case, right? The student thinks that the equal sign means the answer. And so the rule that's being misapplied is the equal sign means to find the answer, when in reality, what they need to understand is there needs to be balance on either side. So this rule expires very quickly, but it expires over and over and over again, okay? Particularly if it's not solved in elementary school, when students start hitting algebraic equations, very confused. They're very, very confused. But there is a first grade standard where students are asked to actually find whether or not a statement is true or false when there's an equal sign involved. And so it pretty quickly we can catch it. But this is something I know, at least at my school, that we've talked about with kindergarten and that's why sweet Mirna, who is one of our kindergarten teachers, knows this, right? We've talked about how we need to have balance in the equal sign. And so we've talked about using resources such as this one, which is linked in the presentation. This is a really cool one from Didax. So you can stick that equal sign right there in the middle. And then what you can do is you can hang things on either side. So to show that balance. So I could hang it here to show that 6 equals 2 plus 4. I could also hang it here and I could do 3 and 3 and see that balance, right? I could do 1 and 5 and see that balance. And so this will help students to understand the equal sign doesn't mean the answer. The equal sign means that on either side, things are balanced. It means that things are equal, which we logically know, but unfortunately, sometimes the way we word our problems or the types of problems we're giving students leads them to this understanding, even if we didn't mean to lead them to that, right? So it was unintentional on our part. And that's why we've had this conversation, excuse me, in kindergarten, is because we realized we were unintentionally leading them to that. And so we needed to really think about what kinds of problems we were giving our students so that we weren't setting them up for that misunderstanding. Okay. See, I don't like that. There we go. It makes me leave the, and then the other resource in there is there's also an article about the equal sign. So again, if you want some more information about how to think about it differently, how to do it differently with your students, there's a resource there. Okay. So we have just a little bit of time to do this, but I'm just curious if, as we've been talking, if there are any rules, or maybe you've also experienced these discussions in your school, are there any other rules you're thinking of that you've noticed a student has come to you with, or you've realized later, uh-oh, I was pushing this understanding on them and now this is not going to work for them. It's an always isn't forever situation. If you have one of those examples, feel free to unmute, or if you'd like to share, if you prefer to share it in the chat, you can also do that. But does anyone, I'll give you a moment to think. Does anyone have any examples of any rules that they can think of that might expire? Whoops.
Well, I'm just going to say that I realized that I was pushing the wrong understanding of this math on some, or maybe I was not trying to let them know what was the truth about them, or just letting them think about that like that, because it was easy, or maybe because I didn't have any time to explain, and I didn't clear it out. Okay. Well, thank you.
Yeah, there are a lot of reasons why these things happen, right? I hope that you understand, I'm certainly not trying to imply any of us would do it intentionally, right? We don't want to confuse our kids, but unfortunately, for various reasons, sometimes we don't think to correct it. Sometimes we don't hear the students saying it. And so we don't realize, right? Or we haven't noticed in the work that they're giving us that that is the error. That's the misunderstanding that they have. And sometimes it's our misunderstanding. And sometimes it's us not knowing what's going to come next. And so we don't realize that what we're doing is actually creating a problem, right? And so that's another piece of it. Oh, okay, let's see.
Oh. 10 minutes, Katie.
10 minutes. Thank you, Monica. I was like, okay. All right, so I actually am going to keep going on because I asked Monica to tell me at 10 minutes and I knew what slide I needed to be able to be at 10 minutes. Okay, so this actually leads to my final point. So found this quote. This is from Glenda Lappin, who was the president of the National Council of Teachers of Mathematics. I'm guessing about 20 years ago from when this is dated. I think she wrote this when she was the president. So it says, our own content knowledge affects how we interpret the content goals we are expected to reach with our students. And so when we're thinking about content goals in math specifically, take a moment and think about how our own content knowledge could affect the content goals that we have for our students. Just take a moment and think about that. Share in the chat if you can think of any ways that our own content knowledge could affect the content goals that we have for our students. What are some ways it could affect it? Also, double check that you're sending it to the whole group, because I've gotten a few direct messages I've realized, and people didn't realize they were sending them just to me. What are some ways that it could affect our content goals in our classroom? Yeah, expectations, Ileana, expectations could be raised or lowered depending on our content knowledge, right? If we don't feel comfortable with what we're doing, we may not teach it to the depth or the level that we need to, right? Which could, as Mirna said, limit our students. Yeah, order of operations for sure. Scotty, that could definitely get in the way because there's a lot of operation rules that we saw today. And so if any of those rules are happening, then when we start getting into some order of operations situations and algebraic equations and algebraic anything, that could get in the way. If we don't understand, yeah, Michelle, if we don't understand the math we're teaching, that will affect what our kids are learning. Yeah, Naomi, that's a really great point, though. If we were all taught in a very traditional way, I know that I'd say probably at least 95% of us were. And so unfortunately, that means that we don't always have that really solid understanding. We know what we're supposed to do, and so we just can do it, but we don't necessarily know why it works or how to explain it to our students in a way that makes sense, right? So you guys are coming up with some really great examples. This actually is not the entire quote. So that is the first part of this quote. Here are some ways that Glenda Lappin said that it could affect our ability. So it could affect our ability to explain clearly and ask good questions, right? If we don't realize they have a misconception, we may not be asking the questions that help undo that misconception, right? That help break that misconception. It affects our ability to make those moments happen more often for our students, right? So it affects our ability for the kids to realize that they have a misconception or to think more deeply about a problem. It affects our ability to push each student at that special moment when he or she is ready or curious, right? So if we don't know it at a deeper level, then we don't even know what to ask or where to go with it. And it affects our ability to approach a mathematical idea flexibly with our students and to make connections. And I think that goes back to the idea of, we were taught in a traditional way, most of us. And so I know for me, even as a math coach, there are times that I go to the standard algorithm, the standard way that I was taught, because that's just where my brain goes. But I'm really trying to open up my mind to all of the other ways that there are to solve problems, and that those ways are just as correct as the way that I was taught. And in some cases, and probably in many cases, they're more mathematically sound, right? They have more of a mathematical basis than the rules I was told or the steps I was told to just follow and trust me, right? How many teachers have I had that have just said, just do this, it works every time, you're fine, right? And I didn't know why it worked, but I was a rule follower, so I did it, and it worked. So why would I question it? So the entire article is linked in here if you'd like to go check it out. And then, as Michelle mentioned in the chat, this is again a great example of what Marilyn Burns had said, is that teachers can't teach for understanding if they don't have a firm foundation of understanding themselves, right? Math is in particular an example of that, because we can unintentionally create misconceptions, right? We don't mean to confuse the kids. We don't mean to send them on with rules that are not forever. It just happens because we don't necessarily understand it to the depth that we need to. So thinking about that, and thinking about that from that perspective of, and I wanted to kind of point out, I know that can feel really daunting to say, like, our mathematical ability is going to have, can have a detrimental impact. It is, while it is true though, I do want you to think about that you don't need to become an expert overnight, and that you probably have some great resources at your school in people and in vertical teams of people who can help you understand the math better if there's a particular piece, or to even just have conversations about an upcoming concept or unit to make sure you're prepared with any of the possible things that could happen, right? Sometimes it's just we haven't thought about it. And so having those conversations, so using those people as resources. If you don't have that, or if you would like more information, some really great resources. These are all professional books that I own and highly recommend. So, and again, these are all in the presentation that will be in the resources. But these are the kinds of books that will help you understand the math better, so that when you go to teach it, you can go to a specific concept, particularly in the 3 books to the right, the Math Matters, Understanding the Math We Teach, and About Teaching Mathematics. Any of those, you go to them, you can go to a specific topic, and there's a ton of information and examples, including things that could be misconceptions for students, which is really valuable, right? The things that somebody else has already thought of and said, this is something a kid might be confused by. And then I also just linked in some other resources. The main source of this presentation of the rules we were talking about is from an article called 13 Rules That Expire. We didn't do 13 rules today, so if you'd like to know what the other rules are, if you'd like to, I tried to pick the ones that I felt like were the best for conversation and for us to be thinking about, but we obviously didn't have the time to do all 13 rules. So that's a great place to go. There's, as well as some other resources for content understanding and vocabulary to be thinking about. If you don't know Project Arrow, which is mostly maintained by Irma Anderson, who I for lack of a better term, is a math guru. And her site has a ton of information, almost too much sometimes. But if you go in there and you just start clicking around, you're going to come across some great articles, some great lesson resources, vocabulary, all kinds of wonderful things. And finally, just some resources that I personally like and personally use a lot. U-Cubed is Joe Bowler, and Joe Bowler also is a fantastic resource just for mathematics education. She doesn't necessarily have a ton of resources for just specific content knowledge, but she has a ton of wonderful resources. Math Solutions is Marilyn Burns, who I mentioned earlier. It's her website and her resources. And then there's just some others on there that I felt like were ones that I would want shared with me if I didn't already know about them. So thank you so much for joining me today. I really appreciate you sticking it out and working through it with us. There's my email address and my Twitter. Please feel free to reach out if you have any further questions or if you want to talk more. We have 2 minutes before the room closes. So, right, you're closing it at 10:30 or 11:30, Monica. So we have 2 minutes. Yes. So it may not be enough time to answer any major questions, but as I told you at the beginning, I love to talk about math. So I'm always happy to help. And I can share any resources that I already have, to the best of my ability. So thank you very